So now we are electrochemistry. We are in chapter 4. Electrochemistry chapter. We are in part 4, electrochemical cells. We're going to look at galvanic versus electrolytic cells. A redox reactions involves, we said, the transfer of electrons from one substrate to another, and there's a potential by this motion to generate an electrical current. There's a direct and indirect way of generating such a current. Usually the indirect contact produces a current, but however, the direct contact will not produce a current, it will produce heat. So in order to get a current, first of all, we must put the oxidation and the reduction on two separate sides, okay, or the oxidant and the reductant on two separate sides. We need to separate the place where the oxidation is occurring from the place where reduction is occurring. In direct contact, when we see that with redox titration later, reactions occur in the same reactor between the oxidant and the reductant. In an electrochemical cell, electrons flow from one chemical substance to another, driven by an oxidation-reduction reaction, because it's impossible to have a reaction without an oxidation, a reduction without an oxidation, and vice versa. A redox reaction can be described as two half reactions, one representing the oxidation process and the other the reduction process. So always we must have reduction and oxidation. I can't have one process and not the other. With redox reaction, it is possible to physically separate the oxidation and the reduction half reaction in space, as long as there is a complete circuit between the two halves. As the reaction progresses, the electrons flow from the reductant donor to the oxidant acceptor over an electrical connection, producing an electrical current that can be used, and we can actually measure it. An apparatus that is used to generate the electrical current from a spontaneous chemical reaction, or conversely, that uses an electricity to drive a non-spontaneous redox reaction, is called an electrochemical cell. Redox reaction may occur in a single container or separate but linked containers. كله هيدا كان blah blah blah, and what we're talking about is literally the following. We have an electrochemical cell is a cell that I can put the oxidant and the reductant either into two separate containers, as in this one, filled in a solution with an electrical wire attaching the anode and the cathode. We're going to see what those mean. Remember, Leo is a jerk, so loss of oxidation occurs at the anode, gain occurs at the cathode, and therefore the anode end is the part where oxidation occurs. The cathode part is the container where the reduction occurs, and actually the probe where reduction occurs. Eventually, a galvanic cell is one that will spontaneously have a flow of electrons. So the difference here is we have automatically, when I connect these two cells together with a salt bridge, it means I completed the circuit. That's when electrons are able to flow. Without the presence of a salt bridge, I don't have a complete circuit. It means that there's, like, if I start to flow of electrons here, look at this plop, plop, I'm done. The minute I put a salt bridge, the electrons can flow out and back in, and then it's a complete circuit. Spontaneous redox reactions in such a circuit flow is called a galvanic cell. To do work, we must prevent reactants in the redox reaction from coming into direct contact with each other. Here we have reactants, and here we have reactants and or products, and they are never in contact with each other. Only the electrons are flowing from one side to the other. The half cells are normally separated. Instead, electrons flow from one reactant to another through an external circuit, which is a circuit outside the reaction vessel. This flow of electrons through the electrical circuit is an electrical current. And the electrons don't go inside the solution, guys, ever. we assume يعني بنحط لكم قال إنه electrons are as if they're inside solution. They're always on the compound, never يعني they're always close to the plate, which has the oxidant or the reductant. Electrolytic cells, unfortunately, we don't really talk about them much, مع إنه they are very, very, very useful. We use galvanic cells we use for batteries and generating energy. Which is why they're more important, yes. But electrolytic cells are cells which drive non-spontaneous reactions, okay? And energy is required from an external source for the reaction to actually take place. But very useful. How so? Plating, electroplating, and let's say making silver plating, gold plating on anything is used industrially with electrolytic cells. We literally force the gold to go from one to another area. So if I put a spoon here, a metal spoon on the cathode end and gold on the anode side, we see that metal gold will go by force because it's not natural, and plate, it will go on the spoon, for example, and we get electroplating. Typically, if we have honey, they should be completely separated, a battery, and we're generating a battery. If we have separation, energy can flow and the delta G is less than 0. In electrolytic cells, we add energy. We put for it an external source of energy for the reaction to actually take place. And we have to add that energy for the actual reaction. And usually the reaction, again, is non-spontaneous and the free energy of the reaction is greater than 0. For this course, we will mainly talk about the galvanic electrochemical cells, okay? And right now I will discuss in detail the galvanic cell. The term battery, sometimes they just say battery. That means it's a galvanic cell. Is usually reserved for a galvanic cell that operates as an electric generator. In a battery, chemical energy is transformed into electrical energy. A galvanic electrochemical cell, voltaic cell or Daniell cell, is an electric current generator that can be formed by combining two redox pairs. This combination, made using an external circuit and an electrolytic junction, make it possible to perform redox reactions without direct contact between the species present. I feel like I'm reading and I don't like that, so I need to just, you guys can do that reading part. Let me start with something like this. Okay. The anodes is the part, the area where oxidation will occur. Remember, oxidation is the loss of what? Electrons. Electrons then are lost and they go up through the electrical wiring, and they end up going to the area where the electrons are going to be gained at the cathode. Okay. So this is where the reduction will take place, gaining of electrons. In this case, the electrons do move, but then the reaction actually stops, and there starts to be a buildup of a positive charge on this end and a negative charge on here, because electrons no longer will flow. It starts to flow, but then when the charge builds up, there's no longer any flow. In order to reduce the charge buildup, what we must do is then add this salt bridge. It's a connection where there's a salt between the anode and the cathode. And it's like a tube filled with electrolytes. And electrolytes are any salt like potassium chloride and things like this. So what happens is, in the presence of the salt bridge, just see this. Remember, electrons were flowing outwards, right? Okay, so what happens is positive charge starts to build here because the electrons are going up, coming out of this area. So what happens? Positive charge builds. On this end, electrons are coming in. So what happens? Negative charge starts to be built here. We have a salt bridge, as I was saying, like a potassium chloride. Potassium K plus Cl minus. As the positive charge builds, what happens is some Cl minus comes in here and neutralizes the positive buildup of the charge. Likewise, as negative charge builds, the potassium ion comes in and neutralizes the negative electrons that are built. And this neutralization allows for further electrons to keep on moving, okay, and to flow. The flow continues. This can occur, or we can have a porous disk here, and a porous disk can allow not electrons, but some ions to go from one area to another. So for example, if we have positive buildup here, negative buildup here, and we can have ions already in solution, whether K plus, Cl minus, in solution on both sides. As negative charge builds, what happens? Cl minus goes there, and as potassium ion starts to come here, and again neutralizing the medium so that electrons can continue to flow. And so electroneutrality is maintained, and that's the reason why we put a salt bridge. Make sure you do the reading yourself on this part. We're going to do now an example of how to set up this electrochemical galvanic cell. Okay, and where do we put each half? So here's a reaction, a chemical reaction. Do we see any energy? Do we see any electrons? No, it's chemistry. It's zinc, copper, sulfate. It's a chemical reaction. Zinc solid reacting with copper sulfate, going to zinc sulfate and copper solid. Remember, we mentioned this a little bit before, that whenever I see a metal with a non-metal, I can split him, and we will separate them for now completely into copper. Copper 2 plus, SO4 2 minus. This 2 goes there. SO4 we know is 2 minus. So net, these sulfates are like spectators, and we end up the net reaction is zinc copper 2 plus going to copper solid and zinc 2 plus. Let's split the two half reactions, the zinc together and the copper together, and balance the reactions. Okay, zinc is already balanced. Let's balance the charge, plus 2 electrons on this end. So we have the zinc is becoming more positive, so it's the oxidation, and we can see that electrons are lost as they are on the product side. Copper 2 plus becoming copper 0, that's a gain of electrons becoming, less positive. And if we're balancing the electrons, 2 plus on this end is required to make this part 0, and therefore we can see electrons are gained, indeed reduction. So we found the oxidation and the reduction half reactions. What we will do is physically separate them. We will put the oxidation on the left, reduction on the right. So oxidation on the left. This is the left. This is the right. And the way I write it is I put a plate, and I call him the zinc plate. And I put another plate on this, and that's the copper plate. Okay. These two plates will be connected to some electrical wiring and a voltmeter to connect the wires and to actually read how much energy or electron flow, and the electron flow is the one that's going to cause this voltmeter to actually move and do a reading, and then we could measure how much energy is coming out. Okay. We will connect this zinc and put this zinc plate into a solution and this copper into a solution. Here, the solution happens to be zinc sulfate, which splits to zinc 2 plus sulfate 2 minus, aqueous solution. Of course, solution means I have zinc sulfate in water. And here, copper sulfate is the solution that the copper will be in. All right, we have then when we want this system to flow, I must connect to a salt bridge with the two. And here we have a potassium chloride salt bridge. These are typically plugged with cotton, or usually there's a sieve-like resin on this end, and to allow only these ions, by the way, to flow in and out, and not any other ions to flow in and out. Are we clear about just now the connection? So this is a spontaneous reaction, and the electrons will flow spontaneously. We said, I'm going to erase. The anode oxidation is on the left-hand side, and the cathode is on the right-hand side. When we talk about poles, and they talk to you about poles, electrons, guys, they are negative charges. They always flow towards the cathode, towards the positive pole. So the cathode, this is the positive pole, and the anode is the negative pole. Okay, so an electrochemical process involves electron transfer at the interface between the electrode and the solution. Electrons do not enter the solution. دايما نطلعوا هون. Zinc, he loses 2 electrons, and the electrons don't go in solution, guys. They flow directly within the pole and they go. حتى when here electrons for the copper are gained. So هون عندي الcopper. Copper sits there, picks up the 2 electrons, and when he becomes copper 2 plus on the surface, he leaves and he goes into the solution. Okay. And actually oppositely the electrons دايما موجودين هون على البول ما بيفوتوا على قلب السولوشن. So بيجي الكوبر 2 plus بيسحب 2 electrons and he becomes copper. That's the reaction that's taking place. 2 electrons, he takes them and he becomes copper. The electron compartment in the oxidation occurs is called the anode, and the electron compartment in which reduction occurs is called the cathode. Okay. Are we clear? We should know how to draw this very well. We should know how the electrons are flowing and to which pole they are going. Once we have the cell itself, this is the drawing of the cell, the galvanic cell. We don't want to always draw it. We have what is called a cell diagram or cell notation. And in the cell notation, we have the following. We put the cathode, the anode first, whatever is occurring at the anode, separated by double line for the salt bridge, and then whatever occurs at the cathode, which is the reduction, at the anode, which is the oxidation. If it's oxidation, guys, how is zinc goes to zinc 2 plus 2 electrons. That's the actual reaction that's taking place. And so what we do is we put zinc solid first. We put one line for the change in the phase. يعني عندنا solid to aqueous, but separated by a single line, and that goes to zinc 2 plus. Had the zinc 2 plus, we will put the concentration in brackets. That's all the anode. At the cathode where reduction occurs, the copper 2 plus is gaining 2 electrons to become copper solid. So first I write the copper 2 plus, beside him the concentration, separated by one line by the then the copper and solid. That's how the cell notation is written. So anode first, then cathode, separated by a salt bridge. Now, sometimes, I don't know why, they don't necessarily write them in the correct way. يعني أمرار بيحطوا الأكويس قبل السوليد, or the electrode. دايما typically is always here to put the electrode first, then the electrolyte. Here it's the electrolyte first, then the electrode. Or just look at the equation and put whatever's coming first. That's what I like. I like to write the equation. Whoever's coming first on the equation is the part that's gonna come first. But typically at the ends you see the electrodes, which are the solids in the electrochemical cell. So phases are separated by one bar and salt bridge by a double line. Concentrations are in brackets. You can sometimes put aqueous or gas or solid on each beside each compound. هلا the minute I put concentration يعني it's aqueous solution. The conductor, plate or wire, which connects the external circuits is called an electrode. So the electrodes is the actual, it's these guys, typically the plate, or we could have a zinc wire here. Okay, we call those the electrodes. The surface on which oxidation or reduction is occurring. On the surface is of these electrodes is where oxidation reduction takes place. Anode is the electrode at which oxidation occurs as the electrons are lost. Cathode is the electrode at which reduction occurs as electrons are gained. Salt bridge serves three functions. It allows electrical contact between two solutions, it prevents mixing of the two electrodes, and it maintains the electrical neutrality in each half cell as ions flow in and out of the salt bridge. We can see that all these type of galvanic cells, they generate energy and they could light a bulb and we could use them. So here we have a cell. Let's write the cell notation for this cell that is here. We first look at the left-hand side, and that's what we write first. عندنا at the electrode, it's the iron going to iron 2 plus. So this is the oxidation part. So iron solid goes to iron 2 plus 2 electrons. So when I write the cell notation, I put Fe solid, or the electrode, goes to Fe2 plus. On this end, the actual reaction, I want you to look at the reaction first that's taking place. Manganese plus 5 electrons plus H plus goes to manganese and 4H H2O. In this reduction reaction, where we're going to gain 5 electrons, we have no solid at all. They're all in aqueous medium. If that's the case, then the plate that we're going to put is a platinum plate. We must have a plate. Even this is a neutral platinum plate, it will not get involved in the reaction, but it is where the electrons will flow from one compound to another. All the others, we will put them in what? With a commas separating them. Why? Because there's no phase change. They're all in aqueous. Now, what do we put then first and what second? It doesn't really matter. Okay. Me personally, I like to put it as written بالequation. يعني عندنا manganese or H plus and manganese on this, and then Mn2 plus. Some people prefer just to always leave the H plus, you know, on an end. It doesn't matter. Okay, once aqueuses are together, they're never in the same order as written بالequation. We must separate the platinum from this aqueous by a line. Okay, single line metals inert. Okay, so the inert electrode, like we said, does not participate in the reaction. Any questions on galvanic cell, how to write it, and on the cell notation? أيها؟ نفس السيل نوتيشن؟ We'll continue. You could rewatch it. I think it's basic يعني لا ما sorry يعني. Okay, just rewatch the video and make sure that you get the idea. The main idea is when you write a galvanic cell, always put the anode half reaction where oxidation occurs on the left hand, reduction on the right hand. You must include a salt bridge. In the cell notation, كمان, the oxidation half is on the left hand, reduction half on the right hand, separated by a double line, meaning the salt bridge, and always put the electrodes on the ends typically, or as the reaction is written. هيدي sum of it. If we have some reaction that doesn't have a solid, we use a platinum plate for the electrode. Okay. ماشي. Otherwise, يعني watch it again. مش غلط to rewatch this video again, definitely, because it's mainly theory مش حل. ولحديت هلا actually ما بيجي شيء direct، يعني شيء من هيدا. Okay.